Hello, and welcome to this video of introduction to predictive models on TIMi Academy. Today, I will show you how to assess the quality of a classification or binary model using the ROC and the gain curves, and how those two curves show quite different informations. Binary models are probably the most common models used in data science. They are used to classify records between ones and zero, events or non-events, apples and oranges. They are used absolutely everywhere. In finance, they are used to classify good versus bad credit customers, for example. In marketing, they are ubiquitous to determine the difference between churners and non-churners, loyal customers, non-loyal customers, customers likely to respond to an offer, or customers not likely to respond to an offer, customers who will need to buy a particular product this week, or customers who will not need to buy this product this week. This is also the type of models used to classify spam versus normal email, or even patients who need urgent care in terms of dialysis versus diabetic patients who are likely under control. All those are binary events, and they can be modeled with a bunch of algorithms. This goes beyond the scope of this introductory video, and if you're interested in learning those algorithms, you will find other videos on this site, like Introduction to Classification Algorithms, referenced in the links below. The model, of course, will make mistakes. If you have a perfect model, your model is most likely wrong, unless what you're trying to predict is something incredibly deterministic. For example, if your model is attempting to approximate an exact mathematical function or reproduce the results of another model, then you might have a model with zero error. If what you try to predict is human behavior or any random event, you cannot expect to have anything close to a perfect classification. So, how do we know if a model is good or if a model is bad? Which KPI are we going to use to assess the quality and the predictive power of a classification model? The first one that is usually taught is the famous classification table. As its name states, it shows how categories are classified after the model. We see how known classes or categories are classified by the model. Rows, in this case, are the known classes, and in the columns, we will see the predicted classes. Let's consider a model with two classes, ones and zero, a binary model. In our training data set, we know what those classes are. This is what we use to learn. So we can organize a table with a count of these records in a very simple table, where we match the predicted classes. We will then have true positives, 1 predicted as 1, true negative, 0 predicted as 0, a false positive, which is a 0 predicted as a 1. That is, in our learning data set, that was a negative case, but the model misclassifies it as a positive. And then we have the false negatives. This is an actual 1 in the learning data set, but the model classified it as a 0, as a negative in the applied data set. Again, we should expect this type of errors, because the model only tries to find something that is common in the data. It finds laws. And we cannot pretend to have a model that classifies perfectly unless we have a very particular situation. But this table has quite some other issues. The first issue of the classification table is that it shows us a very static way to assess a model. It considers that there is only a unique threshold to split between 0 and 1. A threshold that tells us that anything below x will be negative and anything above x will be positive. Usually, if the data is balanced, this threshold is assumed to be 50%. In reality, it can be anything. Often, we just use the a priori probability. In this case, we use 6% as it is the a priori of our heavily unbalanced data set. And you will see with experience that nothing is balanced in real life. As we change the threshold, we can actually plot the relationship between true positive and true negative in a two-dimensional chart like this one. As we start changing the threshold, we see that the points are moving between two extremes. On one extreme, if I put my threshold at 0, anything with a non-zero probability will be a positive, will be a 1. All my cases will be properly identified, of course, but I will also have roughly 100% of false positive. completely useless model. On the other extreme, I can consider that only a probability of 1 will be good enough. And I will pretty much reject everything. In this case, I will have 0 false positive, but a very, very low score of true positive. Basically, I'm at the 0 point. I have another useless model. As we move the threshold between those two extremes, we will have the very widely used ROC curve. Now, this ROC curve is the most used curve, but it also has a problem. And it will become obvious once we start looking at the classification table in terms of numbers instead of percentages. We have here two tables with basically the same information. One expressed in terms of record and the other one in terms of percentages. And those percentages are very, very misleading when we have unbalanced data. To read this, let's look at the first row. We had initially 6,543 records tagged as 1, or true. They are our target values. This model properly identifies 5,230 of them as positives in this top 10%, leaving only 1,113 as negative. The real problem is actually on the second row, on the negative cases. In most situations, we will have a very unbalanced data set, as I mentioned. That is a data set in which the negative cases heavily outnumber the positive cases. Here, our 10% of false positive actually amount to over 9,000 cases. While we thought our model would be 85% accurate, we see that we have an error rate of around 64%. This is what Eric Siegel refers to as the accuracy fallacy. It means that although it looks like our model is right over 80% of the time, and again, this is a very good model, but we can expect it to be wrong over 60% of the time if we take our top 10% to launch a campaign or take a decision. To avoid falling in this trap, I prefer using the gain curve, because it gives me a better understanding of what this percentage of bias will be. Let's take our roughly 100,000 records used in the building the model. Let's take the roughly 100,000 records we have in our learning dataset. In it, we also have about 6,000 targets, or 6% of the dataset. This is called the a priori probability. After building a model, we have a probability associated to each record, so we can sort the data and put it on the x-axis. On the left, we have the records with the highest probability, and on the right, those with the lowest probability. Then, on the y-axis, we will plot how many of the 6,000 targets have been properly identified as we move down the dataset. This corresponds to the accumulated sum of probability. We can then plot what a perfect model would look like. A line in which each record on the left of the axis, the top probability of the dataset, is correctly identifying a true case. After reaching the a priori probability, in this case 6%, it becomes flat as there are no records left to correctly identify. So my top 6% records are all properly identified as a 1, and my bottom 94% are correctly classified as 0. There are no errors. This is a perfect model. The other extreme is a line at 45 degrees, which represents a random model. If we select any sample in the dataset, the probability of finding true records will be random. For example, if I take 50% of the dataset, I will have 50% of the targets. If I take 80% of the dataset, I will have 80% of the targets. Then we can plot our model. It looks very much like the ROC curve, except it will never touch the y-axis. The AUC of the gain curve is a ratio between the model area and the maximum area, and it is equal to the Gini index. We can also plot the probability curve, and this is really important to properly interpret a model. We now see very clearly that in our top 10% selection, we may have identified 82% of the total positives, but we also have 80% of negatives in our selection, and there are no way to tell them apart. This is how predictive models work. If two individuals have the same characteristics, they will have the same probability score, regardless of their future actions. There is another important difference between the AUC of the ROC curve and the AUC of the gain curve. In the ROC case, the entire area under the curve is computed, but the lower triangle actually explains nothing. So while we may be tempted to say that the 80% of the AUC of the ROC curve explains 80% of the data, reality is quite different. With the gain curve, we only use the upper triangle, meaning that we can interpret the AUC a little bit like the R-square, although mathematically speaking, they are both very different. In summary, remember, models are supposed to have errors. A high AUC does not mean the prediction will be correct most of the time. It will mean that the model is doing much better than random. It still will make errors. Try to use the gain curves instead of an ROC curve to get a better feel of the classification error, and use Gini instead of the AUC of the ROC to get a more insightful KPI. I hope you found this video interesting. Don't forget to subscribe. Look for more videos on TIMi Academy, and thank you very much.